In this video, I'm going to show a very simple first example of running a transient analysis in HSPICE. We analyze an RC circuit given by a time-independent voltage source and look at the waveforms in WaveView. First, we have here the settings or the netlist already built. So let's start with the voltage source. I'm using a PWL, which is a piecewise linear source, which lets me define the voltage as a function of time. And here we have VS0 PWL, and the thing that you guys can see here inside the parentheses are let's get the parameters for the PWL. This means that at time 0 the voltage is 0 volts, and it stays at 0 volts until 5 milliseconds, and at 5.001 milliseconds it sets up to 5 volts, as you can see here, and it stays at 5 volts until the end of simulation, which takes in total 10 milliseconds. The small difference between 5 milliseconds and 5.001 milliseconds, this difference will create a step instead of an ideal discontinuity, which helps the simulator. The source is connected between node VS and node 0, which is ground, and in HSPICE, node 0 is basically always the global ground, as you can see here. So after that, we have this resistor, this 1 kilo ohm resistor, which is between the source and the output node. This resistor limits the current, and together with the capacitor, it defines the time constant of the circuit. Let's now look at the capacitor, and this capacitor will be between the output node and the ground. So here we have a 1 microfarad capacitor, and this capacitor stores charge and causes the output voltage to rise gradually instead of instantaneously. And this capacitor, together with this resistor, since we have 1 kilo ohm for the resistor and 1 microfarad for the capacitor, this will result in a time constant tau of R times C, which will then give us 1 millisecond. Let's now look here at our transient analysis setting. Here the time step will have 10 microseconds, and the total simulation time will have 10 microseconds. We'll have here the time step will have 10 microseconds, and the total simulation time will have 10 milliseconds. As we can see here, point trend 10 micro and 10 milli. So the first number, 10 microseconds, is the time step used for saving data, and the second number, 10 milliseconds, is the total simulation time. This gives us enough resolution to clearly see the RC changing behavior. That's why it was set in this way. And then we have here this probe, and this line is very important, as it tells HSPICE to save all node voltages during the transient simulation. And without this probe, WaveView may show simply a flat line, or it's gonna give you completely empty waveforms, even if the simulation ran correctly. Therefore, it's very important to have this probe here. And then we have here this enable post-processing output. This simply gives us the results that can be viewed in WaveView. And finally, we have here the .end, which you guys will always see at the end of every HSPICE netlisting. So this is our netlisting for the simple RC circuit. Let's then move to the simulation. I'm gonna open now HSPICE, and here I have already everything set. So this is the environment I'm gonna be using to run my HSPICE netlisting, and you guys have to firstly make sure that you have your netlisting in the right folder. Let me go back and alright, so since I'm in this directory, I have to change firstly my directory and check where I have my net listing. Now that I'm in this directory, the net listing that I just showed you guys is this file, the one that ends with extension SP. This is the most important file, and you have to be familiar with these two files because this one and this one that ends with list extension, because you're gonna need these files basically most of the time. Let's now run firstly this file, the one that has the SP extension, and then we're gonna see what will be the results. These are the results that I already got after running the net listing. So you're gonna type HSPICE -I, and then you're gonna write the name of the file that you want to compile. We are working with this one, simple RC circuit SP, and then you're gonna see this, and this simply means that the compile was done without any errors. And here you're gonna see your secret statistics, and basically here we will find all the, or at least main information related to your circuits. And here you will be able to check that everything is working, because you say the job ended at, and it gives you the time. But if there was any problem with the circuit, you will see that it would print you an error message or a red message. In that case, you would have to double check your work. So we're gonna also check this circuit, or we're gonna do the circuit analysis, the trace analysis using the WaveView, because as you can see at netlist, it's pretty hard to completely grasp everything just looking at this. These are just letters, and the format itself is not very user friendly, so that you guys can have an idea of the kind of circuit that we are working on. Let me show you the circuit that I built in HSPICE. So this is the circuit in HSPICE, and what we have here is exactly the same as what we have here. So this whole net listing is describing this circuit, and here you can see the VS. This is the node that comes from the voltage source. This is the node that connects to the resistor, and then from this node is gonna connect to this node connects to the capacitor. So what we have here is exactly the same that we have here. This is just expressed, in a format that we can run in HSPICE using this netlist and everything. So here we have exactly the same setting, and if you were to run this using HSPICE, let's see what we would get. And then we also analyze using WaveView in HSPICE. So with HSPICE, we see this. This is the output waveform that we are getting with HSPICE. And now let's also check that using simply HSPICE. Now going back here, let's then open WaveView, which is the main wave analyzer when you are working with HSPICE. Let's then open WaveView. And you can write this. It's gonna work, or you can also have a space in between WV and the sign. Here it's gonna show up on some of the projects that I've been working on. And let's now open. Oh, before doing that, it's very important to do something first. If you notice, after you run HSPICE, after you run this command, you will not see all these files immediately. So you have first to generate these files using this command, HSPICE. -O, and this will basically means output. And after you run this command, these files will be output. So you're gonna need these files to do many of your circuit analysis. Therefore, it's very important to have these files as well. So after you compile your netlist, and you have to run this as well so that you get all these file output. And then we can open the WaveView. We have it already here. So when we check here, open waveform, you're gonna see all these files. And the one that you're gonna use to analyze your waveforms will be this one that ends with TR0 extension. So let's click on it and okay. So here you will have to expand this and then click on this option, top level. After that, we will be seeing this environment. So on the left, we can see the available signals. For this circuit, HSPICE save the voltage at each node and also the current through the voltage source. Let's then begin by analyzing each one of them. Firstly, I will plot Vs, and as you can see here, it is a stepped function. This is the voltage at the node connected directly to the voltage source. As expected, the waveform stays at 0 volts until 5 milliseconds, as you can see here. At this point, it's gonna start at this point. And then it steps up to 5 volts, just like we said before. And this matches exactly how we define the PWL source in the net listing. If I zoom in, you can see here the transition clearly around 5 millisecond mark. Let's then zoom out. And let me now explain VO, which is the voltage at the output node. So this is the voltage across the capacitor. Unlike the voltage source, this waveform doesn't jump instantly. Instead, it rises gradually, following an exponential curve. This is the classic RC changing behavior with a 1 kilo ohm resistor and a 1 microfarad capacitor. The time constant is then 1 millisecond. So the voltage approaches its final value, as you can see here in this plot. And you can use the dots like this, or you can have all of them kind of overlap. Let's just to put this on top of the other, as you can see here. But I just wanted to first explain it separately so that it becomes clear for everyone. Let's now check this plot. All right, and here you can see the current flowing through the voltage source. Right after the voltage step, the current is at its maximum because the capacitor initially looks like a short circuit, and as the capacitor charges, the current decays towards 0, as you can see here, which is exactly what we expect in an RC circuit. So the current is gonna start here at its maximum, and then when it gets to this point, it drops to 0, and then it's gonna go back again and go to its maximal state again. And this plot simply shows the 0 ground node. This node 0 is the global ground in HSPICE, so its voltage is always 0 volts. And that's why this waveform is just a flat line at 0. And usually it isn't very interesting to plot. So we can delete this one. And or we can have it overlapping. And here we see Vs at the input node and VO at output node. So that's it. And we're gonna go deeper into the analysis and how to use the WaveView and everything. This is just to do our first analysis using our simple RC circuit.
In this example, we are going to analyze a more complex resistive network using HSPICE. The goal here is not transient behavior, but how to compute the transfer function, which simply means how the output voltage behaves with the input voltage. But before doing that, let's first save this netlist. Let's save this as R network SP, and then all files, save. Let's then open this in HSPICE. We can simply upload it, our network, and we have it here. Then let's first run this. Alright, everything seems to be working fine. Let's then generate the output files. As you can see here, we don't have the output files yet. Let's first call the output command. Now if we update this, we can see here all these files were generated. Just to check, we can also use ls, and we can find it here. Let's then go back and start analyzing what we have in this netlist. So here we start with a DC voltage source of 1 volt. Using this 1 volt voltage source is very convenient because it makes the gain interpretation straightforward. And the source is connected between node VS and node 0, which is the global ground. And then we have here this resistor network overview. In this network, the resistors are connected between several internal nodes. Rather than analyzing this by hand, we will be using HSPICE to solve the node voltages for us. After that, we have here this small division, right? The middle branch, the upper branch, the output load, and so forth and so on. But let's start first in this part, in the input branch, where we have R1 and R2. So the input voltage at node VS feeds into node 1 to a 1 kilo ohm resistor, and then into node 2 through a 500 ohm resistor. But perhaps it will be nice for us to look at the circuit. And I have the circuit here in HSPICE so that you guys can get a better understanding of what is going on here. We have here node 1, 2, 4, VO, which is the output node, and 0 and 5. So we've already talked about node 1, but now looking here where we have R3 and R4, so this is node 2, and from node 2 the circuit splits. One branch goes to the output node VO through this 800 ohm resistor, and the other branch goes directly to the ground to a 200 ohm resistor, R4. This creates a loading effect that influences the output voltage. And if we look here at this part in the upper branch, there is also an alternate path from node 1 to the output ground through node 4. And this path consists of this 1.5 kilo ohm resistor followed by this 700 ohm resistor. Multiple paths like this make the circuit harder to analyze manually. That's why we will be using HSPICE to compute this for us. And last we have this output load, and at the output we model a load using two resistors. These 100 ohms from VO to node 5, and these 900 ohms from node 5 to ground. As you guys can see here, the middle branch, the upper branch, and the output load is exactly what we have in this schematic. So in this branch, or having this configuration now, R7 and R8 effectively creates a 1 kilo ohm load at the output, and this affects the final output voltage. Let's check this part in the net listing. So this part, the transfer function analysis part, this line is simply telling HSPICE to perform a transfer function analysis. Basically, what we are asking here, we are asking HSPICE to calculate how the output voltage at node VO depends on the input voltage source VS. And mathematically, there will be the ratio where we have, V out over V in. So we will be finding that using this command. And because the input voltage has a value of 1 volt, as you have already noticed here, the input voltage has a value of 1 volt, the gain is numerically equal to the output voltage itself, right? And in addition to the gain, HSPICE also computed the input resistance Cn by the source and the output resistance Cn looking into the output node. Let's then check the results. Alright, the results will be printed into the HSPICE output file. The DC gain tells us how much the circuit attenuates or amplifies the input signal. The input and the output resistance give us insight into how this network would interact with the other circuits connected to it. And just to let you know that since this is a transfer function analysis, there are no time domain waveforms, and that's why we don't really need to plot something using the WaveView this time. Instead, we're going to simply do an analysis based on the numerical values reported directly by HSPICE. And we can get them using this file that was also outputted, the one that ends with list extension. Let's then open it. So in this file, we have all the important information. And as you can see here, we have V out over V in, and this is the result of our transfer function. Here we have some more details, the input resistance at Vs and the output resistance at V out. And that's it, we are done with our analysis. So just to wrap up, in this example we use HSPICE not to simulate signals over time, but to extract important small signal properties of the circuit. And this kind of analysis is extremely useful when evaluating gain, loading effects, and stuff like interface behavior between blocks. So we are done with it, and I hope you guys found this to be helpful. Alright, in this last example, we're going to perform a pulse width analysis using HSPICE. And the pulse width analysis helps us understand the frequency behavior of a circuit by identifying where its transfer function goes to 0 and where it becomes infinite. Let's begin by saving this. Let's call it high pass circuit, or better, let's call it high pass filter. And then let's upload it to HSPICE. We have it already here. Alright, everything seems to be working fine. Let's then Alright, and we have already generated the files we're gonna need. Let's then start analyzing our netlist. In this first part we have the AC voltage source, and we start with this voltage source with a magnitude of 1 volt. The AC value is used for small signal analysis and doesn't represent the time domain waveform. Using an amplitude of 1 volt again makes the interpretation straightforward, and we don't need to stress too much to solve the problem. After that, we have the capacitor. The capacitor is connected in series between the input node and the output node. The input node, that is Vs, and the output node, let me show you here. So the circuit is pretty similar to the one we used in the first example. And here I simply changed the order. We had the resistor first here, and now I just changed it with the capacitor position. And so at low frequencies, the capacitor behaves like an open circuit, blocking the signal. And at the high frequencies, as expected, it behaves like a short circuit, which will allow then the signal to pass. And we have here this resistor, and this resistor connects the output node to ground and provides a path for current. Together with the capacitor, the resistor form a first order RC high pass filter. And that's why we have these two elements here. Looking at the net listing, we see that we use this line to perform our pole zero analysis. So what this line is doing is that this line is telling HSPICE to perform the pole zero analysis, which is basically to find the poles and zeros of the transfer function from the input source Vs to the output voltage at node Vo, as we saw here. And in other words, HSPICE is analyzing the ratio of the output voltage to the input voltage. Since we're already done with the simulation, we can then move to check the files that were generated. And for this circuit, we expect a very simple result, which is 1 0 at the origin caused by the series capacitor, the one seen here, and one real pole set by the resistor and capacitor values. Let's then open this file. And as we can see here, we have the pole zero analysis. And as expected, we have one single pole and none zeros. And this is the signature of the first order RC high pass filter. The pole frequency depends on the resistor and capacitor values. It is equal to 1 divided by R times C. With 1 kilo ohm resistor and 1 nanofarad capacitor, the pole is expected to appear approximately at 1 megahertz, as we can see in this result. And if you look at this part, you will see that there are no zeros, but actually there is a 0 at the origin. And the 0 at the origin explains why the output voltage goes to 0 at low frequencies. At DC, the capacitor behaves like an open circuit, and therefore no signal reaches the output. That's why there is none zeros here, but actually there is one at the origin, and that's it. And why would be interested in this kind of analysis? Well, the pole zero analysis gives us a compact mathematical description of how this circuit behaves in the frequency domain. And the frequency domain is one of the very known domains that we'll be using all the time whenever we want to perform such a kind of analysis, and when we want to understand the circuit focusing in some particular aspects. So just to summarize what we did, in this example, we used HSPICE to extract fundamental frequency characteristics of the circuit. And this technique is very powerful. That's why I thought it would be interesting to practice too. So we have come to the end of our examples. I hope you guys found this to be helpful. Thank you.